Hello everyone, and welcome to this video and also new series. Indeed, I start a new series where we will discuss about paper in quantum computing. And in this video, we talk on the paper title toward molecular docking with neutral atom. This is the paper and some of my note, and we talk about this paper today. The paper was written by Mathieu Garrigues, Victor Onofre, and Noé Bosc-Haddad. You can tell from the title, this video is about the use of quantum computing in chemistry. More specifically, we talk about molecular docking, a key technique in drug discovery. Molecular docking is a computational method used to predict how two molecules, typically a drug, collect a ligand. So we have this molecule, a drug. Suppose this is our a ligand, and a target protein collect a receptor. A target protein collect a receptor. So these have interact with each other. The goal is to interaction of each other. The goal is to find the best way for the ligand to fit into the binding site of the protein, much like how a key fits into a lock. So in this paper, the author begin by show how the docking problem can be reformulated as a graph problem. After a brief overview of neutral atom quantum computing principle, they explain how the problem is encoded for a quantum computer and propose a function to evaluate the quality. This is to propose a function. Yes, a function for evaluate the quality of the result. They implement three different approaches to solve this new graph-based version of the problem. The main contribution of the paper is the three approach. Is the third approach, which is based on machine learning. This approach. The paper starts with the construction of graph for the molecule involved in the docking process. Each molecule has favorable point where it can connect to another molecule, and each possible connection has its how interaction strength. So by linking these favorable points, we can build show there as show there. We can build a graph called the binding interaction graph. A good docking corresponds to the case where we have a maximum number of favorable connections. So we have the two molecules in the docking. Then we have a graph that represents each molecule. And for each molecule we have some point called pharmacophore point, because we have these two, for instance, there, one there, and pharmacophore one which another color. We'll take this like this, like this. So during the binding interaction, you can have some connection which to the point, and that this gives us a new graph. So the binding interaction is in terms of graph theory. This means finding the way um, maximum click in the binding graph, binding interaction graph. To solve this well-known graph problem, the author chose to tackle in complementary version. The complementary version of this problem is maximum Y independent set problem, because this one is suitable for the neutral atom quantum computer. So now we talk about a neutral atom. Quantum computer. For solve the MIS problem, the author chose to work with a neutral atom device developed by Pascal. This device is designed for analog quantum computing. In this device, the qubits are the Rydberg atom. The author highlights the important parameter from computing in this device from Pascal. The register, as the register it means how the neutral atom is configured and trapped by a laser pulse, and the channel, the channel is how that consists in laser pulse used to manipulate the register. It is characterized by the some variable that we see there's variable later. For the maximum weighted independent set problem, the graph is directly mapped onto a neutral atom network. However, sometimes an issue there's an issue. Some non-local interaction cannot be represented in the neutral atom setup because interactions are limited by the Rydberg radius, which is normalized to 1. This restriction gives us what's called a unit disk graph. To overcome this limitation, the paper proposed adding auxiliary atoms to create indirect connection between nodes that are too far apart to interact directly. So, for example, suppose we have a two node in our graph, but in the quantum register they cannot have the connection between these two nodes because they are too far apart. So what we do, we add an auxiliary qubit between our node for create a connection for create an indirect connection between these two nodes. Now, after properly embedding the MWES problem, the author focused on the algorithm used to solve it. In this case, they use a quantum algebraic algorithm, QAA. The basic idea is to start with a simple Hamiltonian, one whose ground state is easy to prepare, and then slowly evolve into the Hamiltonian that encode our actual problem. The goal is for the system to stay in its ground state throughout this evolution. If the process is slow enough, the algebraic theorem ensures that the system will end up in the ground state of the final Hamiltonian, which corresponds to the solution of our problem. The crucial part of the QAA is tuning the Farabi frequency and the detuning with the associated parameter, the rise time, fall time, initial and final detuning. So one of the key contributions of the paper is the optimization of these parameters to improve the performance of the algorithm. The first method showcased for the MWES problem is the IP-up VQEA. According to the paper, this method is an extension of Bayesian optimization. However, the author does not go much further into this approach. Instead, they focus more deeply on the machine learning part of their work. As IP-up takes more time as the size of graph increases, the author suggests using a machine learning model trained to deduce suitable parameters for a given graph. The training data is generated by running IP-up to solve the VQAA for different graph configurations. The author chose to predict each parameter separately. The result of the machine learning approach was not very good, according to the author, mainly due to the lack of training data. However, the results are still promising because the advantage of the machine learning approach is that it offers a way to generate parameters for the pulse without optimization for each graph, as is done in VQAA. Also, the paper showed that we can find a solution close to the optimal one, which can be good enough for drug discovery. As mentioned in the paper, so with a larger amount of data, MLQAA for machine learning quantum algebraic algorithm could become a powerful method. This is the end of this video. Thank you for your watching, and we see you for another paper in quantum computing.